So for example,
so phi naught is just to shift the phase to be accurate with the graph.
correct,
Or you could use negative.
correct. So let's say we have this graph. This minimum point's at negative 10 centimeters. The maximum point is at positive 10 centimeters. Peak to peak is 5 seconds. Let's write the equation that describes the motion of this particular object over time. So number 1, what is A? 10 centimeters. Now the 5 seconds represents the period. So what's the frequency? 1/5. So what's omega? 2 pi times the frequency, so 2 pi over 5 radians per second. Now, like we just said, phi naught, if we want to leave our function written that way in terms of a positive cosine, phi naught needs to be pi. To shift it from a positive maximum value to the negative maximum value, the difference is pi. So the function that describes this particular graph would be 10 centimeters times the cosine of 2 pi over 5 t plus pi. That's a 5, not an S. So that equation would accurately describe the motion of that graph. Another way to accurately describe the motion of that graph. I know if I start at a maximum negative value, then it's a negative cosine function. So I can also write it this way, as negative 10 centimeters cosine of 2 pi t over 5. Those are equivalent equations. They are the same thing. If I have a positive cosine of our 2 pi t over 5 plus pi is the same thing as negative cosine of just 2 pi t over 5. They're identical solutions. Okay? So the phi naught, you only need to use that if you want to leave it in, say, cosine, and it's not an exact cosine function. If you know the type of function it is, if it's sine, cosine, negative cosine, you can just write it as that type of function without the phi naught, and that's fine. It doesn't change anything. Okay. Questions on that?
How do you spell phi?
P-H-I? Okay, if this is the equation that describes the position over time, what will the velocity be as a function of time? Pretend I'm deaf.
Maybe it's not the derivative, I don't know. Could be the derivative.
Basic relationship.
Maybe the derivative.
Derivative of position with respect to time is velocity. So let's take the derivative of this. We're going to still have the negative 10 centimeters. derivative of cosine, negative sine, of all the same stuff. But then we need to take the derivative of the inside stuff, so with respect to time. Negatives cancel. This 5 will make that 2. So our velocity as a function of time will be, let's see, 2 times 2, so 4 pi. Now remember, this 2 pi over 5, what units did it have? Radians per second. So we now have centimeters per second. And then the sine of 2 pi t over 5. That will be the velocity of our object as a function of time. What does the 4 pi centimeters per second represent? The stuff in front of the sine term. It's an amplitude of sorts. So it's the maximum what?
Velocity.
It's the maximum velocity. That's the fastest our object will ever go. So that's V max. Whatever is in front of your sine or cosine function is always the amplitude. It's the maximum of whatever that function is describing. Okay? We could take this one step further. Acceleration would be the next derivative. So the nice thing is this allows us, having this equation, allows us to find the position or the velocity or the acceleration at any point in time. We just need to plug in the time we're interested in. Please keep in mind, since the 2 pi over 5, the omega has units of radians per second. When you plug your time in seconds, you're going to have units of radians. So when you take the sine or cosine of this, your calculator needs to be in radian mode. If this inside stuff has units of radians, then you have to be in radian mode in order to get sine and cosine out.
So with that velocity, there's the time, so you can plug in the time, you're saying, and then find out what velocity is that at any given time.
Exactly. Anytime you want, you can find the velocity at that time. Exactly. And the same would be true if we took the next derivative. We would have another function with respect to time. Plug in any time we want to find the acceleration.